Okay, so let's get started. This morning we will discuss how to set up a coding environment. We will be using the test project that we have, which is pcoffee, which you have on GitHub, you can see. You will learn how to fetch it from GitHub and fork it this afternoon. So for the moment, we'll just consider that I got it from someone who gave it to me like on a USB stick. And I will basically be using this project to demonstrate how to set up the environment during the morning. And this afternoon, during the exercise session, you will be repeating the process to do it for yourself as well. Everything that I'm going to say is inside the S3 2026 lectures repository. So if you want to follow through the notes as well while I present, you can. You just go to the GitHub. Here you have the link to the site. And we will be here coding environment and IDE for the first part, and the remaining of the lecture is the 2 hours subsections. So if you want to follow through, you have the notes here. I will also follow the notes on my own. I have them open here, so I can copy paste some comments that I don't remember by heart. Okay, so let's say I'm starting my PhD. So I just started. I joined my lab. I receive my computer, I talk a bit with my supervisor. He tells me, okay, you will be starting with the work of a previous PhD who successfully defended his thesis, and then he left the lab 6 months ago. So we have his work saved on an archive. He gave it to me. It's one directory with a few files inside, which I just copied here. So this is basically the content. Go ahead, try to replicate what he did. That's our first task. So inside we have 3 files. So there's a README. Maybe we can start by having a look at the README, see if it explains a bit what the project was doing, how it was implemented. So we don't have much information, at least a link to like a reference that maybe we can look at to see what it's talking about, but not much, and no instructions on how to set up the project, how to develop, do we need to have dependencies or not, we don't know. Okay, so no documentation. That's a bad start, but that's life. What else do we have? We have the CSV file, coffee productivity. So if we look a bit at what's inside this, it seems to be a data file. CSV is for comma separated value. So we have apparently 2 columns separated by the comma, one for the cups of coffee, we suppose, that people drink during a day, during a week, during a month, we don't know, no documentation, right? And the other column seems to be the productivity in a metric that we also don't really know what is represented. Right? And finally, we have the main.py, which, probably is the implementation of the analysis of our previous student, right? So if we take a look inside, it looks like this. Python script. So let's assume we know a bit of Python, so we know, what it is. But yeah, not much documentation either in the script. Some things which are difficult to parse, right? And yeah, pretty much difficult to understand what's going on from a first glance. Let's be optimistic. Let's say, okay, previous student must have done a good job, right? So we have just a Python script. Maybe it's easy to run. I will try to run it. Turns out I have Python on my system. So I will just try to execute the script and see what happens. Failed. That's probably the best outcome that could actually happen. You know? We shouldn't run code without knowing what it's going to do. Maybe even if it's not, a malevolent program, maybe it could, try to install dependencies somewhere I don't want to. It could start generating files in a place I don't want to. It could saturate my disk. So usually don't run stuff that you don't know or you don't trust what they will be doing. So now it's complaining that we don't have a module, matplotlib. So if we know a bit of Python, yeah.
From behind.
It's too low.
Yes, you have the micro.
So I can try to speak louder if you want. Okay. Otherwise we can set. Okay, so let me continue speaking louder, and then maybe we can get the mic also set up. So apparently we're missing a dependency, matplotlib. So how do we install dependencies? Python has a dedicated package manager, which is called pip, so we could try to use this, but let's see first if we have it. Oui. C'est allumé, ouais. Is it working? Yes. Okay, perfect. So the Python on our system doesn't have the package manager pip installed. So we could try to install it, I suppose, but maybe we should think twice about what we're thinking of doing here. We have something installed on our machine, which is there for a reason, is that some things in my system are actually using this Python to do stuff in my operating system. So if I go and try to modify things in this Python installation, chances are I break something. Even if I don't break anything, I will not only work on pcoffee project for my whole PhD. Chances are I work on something else. If I dedicate my whole machine to just working on pcoffee, how can I make it work for another project, right? So using your system Python to develop something for a particular project is not a good idea, and it's not what we should be doing. The proper tool to create environments that are usable for a single project is to use virtual environments. So actually Python implements virtual environments built in the standard library. So we could try also to use our system Python to see if it works to make an environment. So let me just think that would be the syntax. Try to make one. Doesn't work either. We are still missing, a dependency. It tells us how we could actually install it. So if we wanted to, we can still make it work probably. But same thing, it's our Python system. It doesn't have the things installed that we may need to create environment because you're not supposed to use it to work on something else that what your system is doing. So let me remove what I just did. And instead of using our Python installation, we're going to use a tool which is going to bring us a Python installation that we can use to work on our project. So there are many tools actually to do this in the Python ecosystem. It's like the virtual environments have been around for a while, and many things have been implemented to try and use it. We can cite pipx, I think. You have the virtual environment that I was trying to use, which is in the standard Python library. It's actually a subset of a package which is called venv, which you can install that has a bit more functionality than what is just in the standard library. You have another module which is called virtualenv, so it's the longer version, which also allows you to use virtual environments. So there are quite a few that we can try. The reason there are quite a few is that they all have flaws, and basically people have been trying to improve things over time, but basically there are different solutions and they are not perfect, let's say. Nowadays, the thing I would recommend to use if we were using only Python implementation and working only with dependencies in the Python world would be to use UV, which is a new Python package management and environment manager. Which is very fast and basically tries to learn from the mistakes of the previous tools to make the experience better. So that's what I would recommend. Should we do only Python in our project? But as it turns out, we're not sure we will be working only with Python. Maybe for some reason, we need to work also on C++ library during our PhD. Maybe our supervisor works with the Conda ecosystem, so he doesn't fetch the dependencies from the PyPy, the Python package index PyPy, but from somewhere else. So maybe we have reasons to use something else. And in the 2010s, sorry, so about 15 years ago, Python virtual environment still already existed, but were not very practical to use. And the data science people, mostly at the beginning, they wanted something better to work with virtual environment. Especially in data science, you like to work with Python because it's easy to prototype things and to make plots, but you also sometimes need performances to analyze huge sets of data. So they tended to have a mix of things implemented in Python, things implemented in something else, and they wanted something to manage these different languages in a unified way. So that was the creation of the Conda ecosystem. Conda is a package specification and was also a package manager at the start that is agnostic of the language. So you can make Conda packages from things implemented in basically whatever language you want. That's the thing. And so in our case, we will be using Pixi, which is a package manager for Conda, which is modern and offers reproducibility guarantee that the previous tools in the Conda ecosystem didn't have. So that's the reason we're using Pixi and not something like UV directly, that we want to be able to use the Conda ecosystem so that if we start working with a different language, we can do the same thing that we do now in Python. And we will be using Pixi for this. So the first thing to set up with Pixi is to initialize a workspace. So Pixi works with workspace. First command would be to initialize it. So it's a pixi init command. What it does is create this manifest file, pixi.toml, which basically is the configuration for our workspace. So after the initialization, there's not much inside. It found my identity by looking at my Git credentials, basically, so it knows who I am. The channels is where Pixi is going to search for dependencies when we try to install them. So the default channel is Conda-forge, which is you probably know about it, it's the default community-owned and managed channel for Conda packages, basically. So it's a very big channel for Conda packages. Some communities, they have dedicated channels, which are very big. You can cite BioConda, for instance. But mostly, like when you do something, you try to put it on Conda-forge for others to use. So the workspace has a name, and it has a platform. So my machine is a Linux 64 platform, meaning a x86 processor architecture. Since Conda packages work for languages that can be compiled, the packages that you create, they contain binary, so they need to run on the platform for which they were created. But Pixi is able to support several platforms at a time and allows you to cross-compile from one platform to the other if you need to. So the first thing we are going to do is we're going to add more platforms to our project so that if we want to work with someone else who is, for instance, using a Mac, then he too can use our project and install the dependencies the same way we do. So the command for this would be, pixi workspace platform add. That's pretty self-explanatory, right? And then we are going to add the platforms that we want to support. So we want to support, for instance, Linux machines that have ARM CPUs. We want to support OS X. OS X also ARM. So that would be the new processor, M1, M2, M3 from Apple, right? And finally, we also want to support Windows. Right. So all this did was basically modify this line to add a few platforms to support. Okay. So now let's try to add some dependencies. Yes.
When we sell for Windows, is there included in Windows 64, or is another platform that need to be added?
That's a good question. I don't know actually. I don't know, Max, if you know.
Sorry, can you repeat the question?
When you use subsystem for Linux on Windows, what platform is used when you run Pixi inside? Is it the Windows one?
It should, in almost all cases, be Linux 64.
Yeah. Okay. Should be
I'm
Linux
not
64.
sure if you have an ARM Windows machine that it will be Linux Arch 64, but I think these are very rare, right? Windows ARM machines are.
Okay. So.
Can you repeat the answer for the mic?
Yeah, sorry. So the answer is it should be using the Linux 64 architecture or the Linux Arch 64 if you have a Windows machine which is running on an ARM CPU, basically. So it's using the Linux platform, basically.
I have a question. Should we follow all of this? Because I'm running a Mac. Should we follow all of this in this container thing in React, or
for the moment, you don't have to follow anything because we will redo this during the exercise session. If you want to, you can try, but for the moment, I will just show it basically and you can practice this afternoon. If you are on a Mac, you should be able to you do it exactly the same way I do, because here we have the OS 64 or OS X ARM 64 platform, so it should be supported for you.
Okay, it works.
Okay, so now we try to add a few dependencies. So what dependencies do we need? We can have a look at the main.py script to see. So we see NumPy. It's a Python library for managing arrays and numbers, basically. So matplotlib that we were needing before we didn't have. Pandas, scipy, okay. Pathlib is inside the Python standard library, so we don't need to add them, and then Seaborn. Maybe there are other dependencies that we need, which are not explicitly stated at the top of the file, but let's just try with this. So that would be pixi add. Let's add Python also, because we want a Python installation. NumPy, matplotlib, pandas, scipy, and Seaborn. So we asked for a few dependencies. Pixi searched for them on Conda-forge, apparently found a set of dependencies that are compatible with each other, and added them to the workspace. So if we take a look at the pixi.toml, it's basically filled this dependencies table, which was previously empty, with some specification of the dependencies, right? So here Pixi, by default, it follows the semantic versioning convention. So it looks at we didn't specify a version for the dependencies when we added them. So it took the latest one that was compatible with all the other dependencies we had. And it said, okay, we want to use this one. We don't want to pin it exactly to the specific version we just found. We want to allow for the new versions to be used if these new versions are not going to break what we are actually using, right? And semantic versioning is a convention on the versions of packages and dependencies, which tells you when things break, basically. So if you increment the patch number, which is the rightmost number, then it should be a bug fix, for instance. So you should be able to use the same version with a bug fix, no issues. If the minor version, so the one in the middle, is increased, it probably means the new feature was added. So if you were not using the new feature before, then you can still use the library. It should also work. When the major version is incremented, it means that they made some change to the public API of their package. So if you were relying on calling a few functions, chances are the signature of the calls changed, and maybe you need to adapt. So that's why we have this kind of constraint. We constrain the version to be inside the major version that we have now, and less than the next major version, basically. Most packages, they follow this semantic versioning convention, but not all, and in particular, Python doesn't, right? You have Python 3. There won't be a Python 4 anytime soon, but when you go from Python 12 to Python 14, for instance, things change and things break. So Python doesn't follow this convention. And you can see here that the bound here is on Python 3.15. So we pin the next minor version of Python. But for things like matplotlib, it's on really the major version. So we had the version 3.something, we pin inferior to 4. Okay. So for Python, it's automatically understood by Pixi, but in general, when you add a dependency, you should have a look how do they manage their version, do they follow semantic versioning, and then you can adapt the constraints on something relevant. Yeah.
But I see that, I mean, we did download something. Don't
Yes.
we download the specific?
Exactly. So if we look at what happened, we have a new file here, which is the pixi.lock. The pixi.lock basically is the guarantee that Pixi gives you that you will be able to reproduce your environment. So if you look at what's inside, it starts by a list of channels from which the dependencies can be fetched. And then you have the list of all the dependencies that we basically requested. So we only added 5, right? But those dependencies had dependencies, which maybe had dependencies, etc. So here we have a list of everything that we need to run the thing. At first, we just have the list of package. It's per platform that we requested. So we not only solved it for like just Linux 64, but for the 5 platforms that we had. And later on in the file, we have basically very detailed information on the packages that are used. So you have the URL from where the package should be downloaded. And you have the checksum of the package so that when you download it the next time, you know that it's exactly the same that you were expecting and you were using before. So this file basically is the key to being able to reproduce your environment. It's the guarantee that you have, now that we do have one, but if you come back in 2 years and you say, I want to reproduce this environment exactly, which is in the pixi.lock, then you can. Provided that the packages are still downloadable from where you should fetch them. So if there is nothing, at the URL of the package, then you cannot reproduce. Conda-forge has a policy that the packages that are put on Conda-forge will stay forever and will not change. They say the packages are immutable. So everything that goes cannot be modified, cannot be deleted. So normally, if you use Conda-forge as a channel, you will be able to reproduce from a log file. As you said, we did, yeah.
If we need a specific version of Python.
Of
Python, for example,
yeah, so, well, I will show it just in a moment with several versions, in fact, so maybe we can just wait. But basically, you can modify these constraints to whatever you need. In the pixi.toml, you can edit the file manually. Or when you do the pixi add, you can also specify the version. I will show an example later. So as you were saying, we did indeed download a few things. So the first thing Pixi downloaded is the channel information, in fact. So at first you download something, it says fetching channels repo data, something like this. So it's like JSON data that describes what packages are on Conda-forge. And since Conda-forge is a pretty big package, it can take a bit of time to download the repo data. Then it's cached and it's faster. But we also actually downloaded the packages. So now we have this .pixi directory. And if I show what's inside, there's an env subdirectory. In the env directory, there is a default environment because we didn't specify a specific environment, so now we are using default. And inside of this, we have basically a Conda virtual environment. So that would be the thing, the installation basically that we will be using is right here, inside this .pixi env default environment. That's the installation we will be using. If you think what we were using before, we were using the Python system. So the Python system was under /user, and if we look at what was there, it looks like this. So you can see it's sort of similar, and that's what an environment means. In fact, it's a set of directories where you're going to put files when you install something, and then the system or whatever knows that if a file is somewhere, then it can be used in a certain fashion. So the binaries go inside bin, the libraries go inside lib or lib64, something like this. The includes go into includes, etc., etc. So that's what an installation or an environment is. And in our case, the virtual environment is a set of directories on our machine on disk. So it's not, I mean, I don't know if the virtual name is very well formed, but it's really something which is there on the disk. Okay, so now we have the dependencies. We can try to run the the picofee script that we had already to see if it works. So there are two ways to execute things with Pixi. First one, which is maybe closer to Conda. For some of you may know Conda, is the Pixi shell command. So it's similar to the Conda activate, basically. What it means is that you activate the environment. So now it takes precedence with respect to your other installation, your system installation. So now, for instance, if I ask which Python would be used, it would be using the one inside the default environment, so in the .pixi directory that we were looking at before. When I did that without the environment activated, it would be using my system Python. So now I have the environment activated, and when I work, it will use, if it can, it will use at the first the dependencies inside the environment. And then if it doesn't find something, it may try to use something on the system. So basically, it's activating the environment makes it takes precedence on your system installation. It's used first. If we look at the Python version, for instance, here we have 3.14, which corresponds to what we had in the pixi.toml, the Pixi manifest, and which is different from the version that we had from the system. If I deactivate the environment and I look at what versions I had, I think it's 3.10, yeah, the system Python. So we haven't run anything yet. There's another command for Pixi to use an environment. It's the pixi run command. So basically, you say pixi run, and then what follows will be executed inside the environment. So the same thing. If I do, for instance, something like this, you see that we still point to the Python inside the environment. What follows the run command is executed inside the environment as if it was activated. So let's try to run the script. The command would be something like this. So pixi run to use the environment, and then we call Python, the one inside the environment, and when we call it on the main script. So now we execute the thing again. Takes a while, but we see things are happening, and we get a plot. So it seems that we managed to make it run. Program is stuck here, waiting for me to close the figure to finish the execution. I want to say that in the real world, just adding a few dependencies and trying to run something usually doesn't work. You have more chances of coming into a project and not having a working environment, even though people are still working on it, but you have chances to come on a project which is finished, and then you try to make an environment and it works. We are very lucky that this thing works, basically. If the PhD starts like this, consider yourself lucky. This is maybe the most unrealistic things about the picofee experiment that you will see during the lecture, right? Okay, so nice. We have a working environment, good. Maybe we want to add a few more dependencies to help us, start working on this project. So at the moment, we only considered the dependencies that were required to run the picofee, right? That's the software dependencies, one could say. But software dependencies are not all, and when you work on a project, sometimes you have tools that you need to work on the project that are not required to run the code at the end, but are required for you to work and be efficient. So that's maybe the distinction you could make between the tools or the project dependencies that you need and the software dependencies that you need. In the Python world, packages can have optional dependencies. So that's how usually they specify these kind of things. They say, okay, I implement a package, but if you need specific tools to run the test, I will make dependency optional, and I will put it in a special definition so that you can only install this when you need to run the test, for instance. So that most users, they don't need the test dependencies, so they don't use it. But if you need it, you can have them. In Conda, we don't have this concept of optional dependencies. It doesn't exist. So we have basically to work around that. And the way to do it is to use several environments for different things, basically. So we have our default environment here, which is just the dependency of the software. We'll try to make a new environment, which is the software plus the tools that we need to have a look at. The way Pixi does this is with features. Features are basically a little piece of environment that you define, which you can then combine with other features to make a full-fledged environment that you can use, like the default one that we had. So we will be adding a feature first that we will call test. And we will use as a tool Jupyter Lab as an example. Maybe some of you use the Jupyter notebooks. So that's a development tool that we could have that would help us prototype. So that's what we are going to use. So we can use the same pixi add command than before, but we will add this flag feature to say that we want to add this dependency, but not in the default environment. We want to add it in a special feature that we will call dev. So if we take a look at the pixi.toml, basically we've added this. We have our default dependency still here, and now we have a feature with tools that we will use for development. For now, this feature is not used in an environment, so it's basically it does nothing. We cannot use it as is. To use it, we need to create an environment that will use it. So we are going to do this. We're going to update our default environment with the feature that we just added, plus the default feature that was used before for the usual dependencies. The command for this will be pixi workspace environment, because we are going to modify the environment. And we're basically going to overwrite the default environment. So we need this force flag here to overwrite the default environment. And then we give a list of features that we want to use. So we are going to use the default feature, the dependencies that we had normally, because in your Jupyter Lab, we want to have the dependencies available. And then we are going to use our dev feature as well, so we can have Jupyter Lab in this environment. And this environment, we are going to call it default, so that it's okay. So we had a warning because the feature was not used in any environment, and now it is. So the warning should be gone, basically. And now we have, yeah.
I didn't catch you about the workspace thing. Could you?
The workspace is basically a directory inside which you work. The pixi.toml configuration that we look at, the pixi.toml file, it's usable in this directory and subdirectories, but not somewhere else. It's the difference maybe with Conda, that Conda you make an environment and you can use them anywhere on your machine. With Pixi, it's in a specific place, which is the workspace, and which is basically a directory and what's inside.
So that means you're creating your directory pk
Yeah.
and you created your environment with the control environment inside in this one, and then you created a new folder, which is the workspace.
No, the workspace is the pcoffee directory that we are inside. It's this directory. We started from the pcoffee starting files, and we have added pixi and the workspace. So now we have it, but it's this directory, the workspace.
So, as we are already inside a specific directory, what the deal of creating this workspace stuff? I don't catch the meaning of this workspace. This is something that is completely virtual for this, really dedicated for the Conda or the pixi stuff, actually.
So the idea of the workspace and the reason why the Pixi people, they design their software like this is that they want to, not to force you, but you push you to have a dedicated workspace configuration for every project that you work on. You can
have several projects inside your pcoffee.
You can do sub-project, yes, but if you work on something completely unrelated, for instance, you're going to make another workspace in a different place, and you're going to use different environment. It's to help you keep things separated and self-contained inside a single place.
And after, it is possible to merge.
To merge what?
Project.
Yeah, okay, so I was not planning to show this, but maybe we can show you if you are interested later on. Yes, you can make, basically, if you work on something which is a monorepo, which is common nowadays, you can have like a workspace, which is the monorepo first layer. And inside your monorepo, you have sub-repositories for different things. And then you have workspaces in each of these repositories as well. And you can work in a place where you use all of them together. I can maybe show you if you're interested later. So now we should have our Jupyter Lab available, so we can try to see if it works, basically. So same thing, we use pixi run to doesn't work. C'est un tiret. Okay. So it works, we have it available, and we could, start working using it like this right away. Okay. Sometimes you want to use several Python versions for your project. You want to check that it works with several Python versions. That's something that we're going to do when we talk about test tomorrow. So what we can do is add a few features to specify the Python version that we want to use in different environments. So we have one environment for Python.13, one for Python.12, something like this. So I'm going to go to the page and copy the commands, so I don't have to type them. Like this. Here we again overwrite the, no. That's what I want to say. We're going to add features that have a specific Python version explicitly stated. So here I add a feature py312, which will have a Python version installed, and we want the Python 3.12 available. I'm gonna add a few of these, one for Python 13 as well. Again, we get the warning because the feature is available but not used, one for Python 14. In order to use it, we are going to remove the Python that we had here in the default dependencies. So we don't have conflicting specifications, right? So I just remove it from here. And now I'm gonna create environment that use these features together, basically to make an environment with the dependencies that we had before and the Python pin version that we want to have it specific. So the command would be a bit long, but it's the same that before. We create a new environment, we override the default. We want the default feature, which is just the software dependencies, but not Python. And then we add the Python feature with the specific version that we want to have. So again, we get the warning because the features are available but not used. I'm gonna make a few of them to show you. Okay, so now what we have is something like this. We have a default environment that uses the default feature, so these, that uses the Python 13 feature, so these. So we are going to have Python 13 in our default environment. And then the dev, so we have the Jupyter Lab also available. We have a production environment, which is just the default feature plus Python, and we choose the Python 13 as the default, so that's our choice, basically. And then we had the same environment, but with a different version of Python, so Python 3.12, Python 3.14, etc., etc. Tomorrow, during the test, you will probably use it to verify that you can run your pcoffee program with different versions and it still works. Yeah.
Having some Python libraries inside the default dependencies, but not a Python version, we create some kind of conflicts between version of the libraries that you're using?
Very good question. So the question is, if we had the dependencies but not Python, and when can we have conflicts between the Python dependencies and the dependencies that we put in our default environment? Can we have conflicts between these requirements, basically, and this one? So the answer is the dependencies, they are not solved per feature, they are solved per environment. So in fact, when you solve the environment, you solve it with all the features enabled together. So Pixi does its job at looking what is required by who and finding something that works for everybody. Sometimes you want environment also to be consistent with one another. For instance, here we have the default environment, which has the dependencies plus Python 13. And if we look at the prod, it's the same thing. We just have the def feature, which is not present. So basically, default is the same environment as prod, or we want it to be, but we just have Jupyter Lab not available inside. We want to make sure that in both environments, we have the same versions of the dependencies that come together. Otherwise, we could maybe develop with our default environment with Jupyter Lab. We do something, it works. Then we try to run it in the other environment, and it doesn't work because we had different versions, in fact, in both environments. So to make sure this doesn't happen, we use this solve group argument, which tells Pixi, OK, those environments are separated, but we want the versions that are in both environments for the packages that are in both sides to be the same. So in fact, it's not solved only by environment, it's solved per solve group, and you can make environment consistent with one another using this. OK, so this was a bit of preparation for tomorrow for the test. Basically, we are ready. We have an environment. We checked the script was working, so we can run it again just to make sure, but it's no reason it doesn't work anymore. Here we use the default environment. When we call pixi run, it's going to check that all the environments are consistent with the pixi.toml file, the pixi manifest. That's why we still download a few things just to install everything and to make sure everything works. But the script is still running, and basically it still works. If you wanted to run it not in the default environment, but in, let's say, the prod environment, to make sure it also works, it would look like this. We just add the -e argument to specify the environment, and now the pixi run, it will run inside the prod environment. We could use another one also to make sure that it still runs if we use Python 12, for instance, like this. This will run using the Python 3.12, the picoffice script. OK. Now that we're ready, we have a working environment. Maybe we want to start, looking at the code and working, etc. So basically, what we need is an IDE. IDE stands for Integrated Development Environment. So basically, it's a fancy text editor. It's something that you will use to edit code, which is text, and that implements features that are supposed to make you faster, more productive when you do this. That's the goal of an IDE, is to make you more productive, right? So here I'm showing VS Codium, which is the fully open source and free versions of VS Code. VS Code has a few parts which are proprietary to Microsoft. I'm not here to recommend you to use any specific IDE. You choose the one that you like the most, right? I will just demonstrate things with VS Code. In order for your IDE to help you be faster, it needs to be aware of what is in your environment. So you need to somehow tell it, OK, I have a NumPy installed, for instance. So you can tell me that I have it available. Maybe you can help me do things with NumPy. So the way to configure it in VS Code is just to specify the Python interpreter. And in fact, we just have to click somewhere here and to tell it to use it. I don't know why it's not happy. I just try to reload. OK. So I will not show you too much about what an IDE can do, because that's something you basically learn with practice. When you do something and you say, oh, it's the first time I do this, maybe I can automatize, that's what the IDE basically is able to do for you. It also can tell you the signature or the documentation of the functions that you call from your own functions or for the functions of your dependencies. If you want to go and have a look at the code, it can also take you there, things like code navigation, etc., etc. So once you've set up your IDE to understand your environment, basically it's able to move inside the environment for you, find the files that you need to look at, etc. The goal is to give you the information that you need when you need it, so you don't have to go look somewhere else in the documentation, etc. Other things that it can do, usually if it understands Python, you can use it to refactor things. So here I have a variable named y. Maybe I want to name it productivity to make it more explicit. So I just told that to my IDE, and in fact it changed the productivity. It also changed it wherever it was used below, right? These kind of things are what an IDE allows you to do to be faster at programming. Most IDEs, they don't come with built-in support for all languages. They have some kind of plugins. In the VS Code Codium, it's called extensions. So I have a few installed that I would advise you to use also for the working on pCoffee. First, to work with Python, there is the Python extension to allow you to set the environment and to understand the Python syntax, basically. Then there are other tools that will be explained probably later in the school. Ref, for instance, is a linter, so it can tell you, oh, maybe your code here is not doing what you think, or it's not written with the best practices in mind. This you will be told about in the quality tool later on, etc. We also have toml files that we didn't open yet, but you have syntax highlighting for toml files, for instance. So if you want to have this, you need to install the extension for toml, etc., etc. So yeah, not much more to say in a lecture like this. I think with practice you will learn how to use it and how to be efficient with it. That's the end of the first part of the lecture, which was about setting up the environment with Pixi, starting working with it, connecting it to your IDE. Do you have any questions on this part of the lecture?
Maybe a question regarding the Python versions.
Yeah.
You have several Python versions for production, for development, etc. That means that it will install each dependencies for the specific Python, so maybe it will be huge at the end.
Yeah, exactly. So you, if we look in the .pixi directory where the environment is installed, we see now we have a few. Since we use the solve group, it's not duplicated every time, but it is duplicated a few times. So yes, this folder can become pretty big if you want to manage a lot of environment and a lot of stuff. Yeah. Yes?
I actually moved to Julia a while ago. I have the feeling this pixi is basically the equivalent what happens automatically. Is this true? Can you confirm basically? Is it?
Well, Julia is a programming language that has its own package manager. I don't know if you can package Julia with Conda, inside Conda package. Basically, I think yes. The goal of Pixi and the Conda ecosystem basically is to be agnostic of the programming language. So for Python, for instance, you have pip and PyPy, which is the Python package inject, which allows you to create environment also and define dependencies for Python, but it's specific to this language. The advantage of Conda and Pixi.
Somehow more automatic in Julia. So I'm not an expert. I hope always that it works automatic somehow, but I see this environment and these tools and so you have them basically get them for free if you start.
I mean, that's a general trend if you observe programming languages, right? Python is very old. It started early in the 90s. So many people started building around package management solutions around it. And then the younger languages like Rust and Julia, many of these problems were solved then by these older languages. with third-party efforts or with concentrated efforts, but many different solutions. So they have experience to draw from to directly implement the package manager in the standard library. And Julia has the package manager in the standard library. Rust also has one standard package management system. The story in Python is a bit more complicated due to the age and it not starting with the package management solution when it came out.
But it means what we learned today in Julia's is somehow done. So I must say I'm a rudimentary user, but of course I also don't want to get involved into too many details, or it wouldn't fit to my time schedule. But I just want to get a short information or statement.
So the point is,
all of the languages have package management.
Yeah, exactly. If your language has one and it's good enough, then use that basically. If you want to mix languages, if you want to work with people that work with Conda already, work with Conda because it's agnostic of the language.
When Julia got started, they aimed at converting people over from Python. So one of the first things they did was develop a very good integration with Python packages. You can call Python code from within Julia, and that under the hood uses Conda to install the Python packages. So there is an integration even with Julia, with this Conda ecosystem to get the Python packages to work. But the Julia packages are handled by Julia itself.
The thing you want to have in a package manager is the ability to have these lock files to make the environment reproducible. That's something you want for reproducibility. And it's not available, for instance, in Python in general thing. In Julia, I don't know. Maybe you have it already, so it's good. But in general, for any science... No, I'm just saying, yeah. If your package manager is bad, maybe you can use Conda and Pixi to make it reproducible and to get more guarantees that what your language could also provide. But in general, if the language has something good, just use that and be happy with it. Yeah.
Is there a way to share environment?
Yes, something I forgot to say, but you will learn about Git in the next lecture. So the way to share things with code is to use Git and platforms like GitHub. The environment we've seen, it's defined with these two files, the pixi.toml, which is the workspace definition, and then the log file, which is precisely in which environment what goes in. These two files, you should check in with Git, put its version control. That way you can share them with people later on. It's part of your...
Question is, if you have people that work on the same project, server, and you don't want to have multiple for all files with can be huge, is it possible to have a place you can have all the environment and you can
Yes.
activate?
So by default, Pixi, they put the environment in the .pixi directory, so it's specific to a folder. So if you work in the same folder, maybe it's fine, but that's not practical. You can configure it to not do this and to install the environment somewhere else. It's called detached environment. And if you use the same configuration with other people, then you can share maybe a few things. There's also a more advanced thing, which is, I think, used in like computing, to deploy environments in computing center, which is to set the Pixi environment storage on S3 storage. And then you can basically share it with the people via the distributed storage also. This I haven't tried, so I don't know much about it, but that's one way to do it.
Is it possible to have a default environment that is shared and the features that are local?
No, I don't think that's possible. Mostly the way Pixi is done is everyone has its own workspace and its own environment, so the sharing is a bit, yeah. Yes?
May you have already explained how to edit a module, but sometimes I need to go inside a module and modify some part like pip editable my module. And where can I find my module to edit?
So for the moment, we don't have a module because we just have the script. That will be the next thing I will be talking about, in fact. So
okay.
Just wait.
So it's possible to make the same thing as pip editable?
Yeah.
Like that. Okay.
We'll see. It's possible to do the same.
Yeah.
Going back to the questions on how
So basically,
just to explain again, the mic is for the audio recording. Okay. Sorry. Okay. So to come back to the previous question, if you give the two files, pixi.lock and pixi.toml, and your source file, you share to someone else without any Git stuff and so on, that means that everybody are able to run your script?
Yeah.
Okay.
The environment is reproducible, so you can remake the same environment. Putting it on Git, you get version control of the file, so you can see the evolution of the pixi.toml. For instance, someone added a dependency, etc. So that's all the benefits of Git, and you should probably use it. But to reproduce the environment, you need the pixi.toml and the pixi.lock, basically.
Which would be the same thing for the UV.
Yeah, exactly. UV does the same with the log file, same thing.
And for the moment, we have a requirement file in some project for Conda, toml file for some py project file .toml for to create make the environment. And now there is a pixi toml file. There is lots of files that describe the environment. Is there a way to manage that, because information can be different in different files?
You don't want to duplicate. So that's the kind of the drawback of Conda, is that since it's language agnostic, you can define dependencies using Conda, but when you work with your specific language for the implementation, you still need to specify things which are related to the language. So the Py project, for instance, we will just add to the pcoffee now to make it a Python package. That's the thing about Conda, is that you use dependencies for Conda, but you still work with a specific language, so you need to have a few things for this language to be set up. Sometimes you want to have both the package available, for instance, in Python for PyPy, so you would still need to put the dependencies in the Py project. That's if you want to make the package for PyPy and to make the package for Conda. There is no very easy way to share between Conda and Python, basically. Sometimes you don't care about the Python package. You just care about the Conda package. So then you just ignore the Python dependencies. That's what you're going to do. But you still have the Py project, so you can make a package of your Python thing, even if you don't specify the dependency. So I will just show it now. In general, it depends how you want to distribute your thing. If you want to distribute with Conda, you don't care too much about the language dependencies. But if you care about both, then you somehow need to duplicate. Yeah.
And how does it fit inside the Docker or Podman environment?
Like anything else, basically. So you make a Docker image, you install Pixi inside, and then you can make an environment inside your Docker image. And then you use it. Yeah, it's nothing special, I would say.
We'll see that next week.
Yeah. Okay.
Can you, just to insist, explain why the log file is important compared to Conda?
Yeah, so in pure Conda, you would be able to do more or less the same, but you don't have the log file. So you define the dependencies basically just with the equivalent of a pixi.toml, so it's something like this. It's a YAML file for Conda, but the content is mostly something like this. What happens is you start working on your project, so you define this, it works, fine. Then some time passes, basically, maybe you put the project on the side, maybe you keep working on it, but the dependencies specification, they are a bit loose. You allow up to the next major version for your dependencies. Normally it should not break, but people make mistakes and sometimes you have problems. So as time goes on, this specification usually is not enough to get a working environment. So it's pretty common that you arrive on a project, you say, oh, nice, there is an environment definition. I will try to create the environment. You try, and it tells you it's not possible. The specification is broken. With the log file, what you get is you decorrelate two things, basically. You decorrelate what you want to depend on the versions because you know features that you need and dependencies you're not compatible with. But inside the log file, you have exactly, precisely, every package that is needed in the environment. So when you come in 2 years from now, you want to recreate the same environment exactly, you can. Because you won't have to solve it again. You already have everything in the log file, all the information, where to get the packages, and what versions, what are the hash of the package. So it's really the guarantee that you get that Conda didn't provide and that Pixi provides, that's why we're using Pixi, is this log file, basically. It's the very precise definition on the environment so that you can reproduce it later on.
It is also possible because Conda-forge didn't get rid of all packages.
Yeah. Well, that's, yeah. But you could also use different channels, and maybe they don't give you this guarantee. So this you should be careful about. For instance, if you use UV and take the packages from PyPy, you can remove packages from PyPy. So you have a log file, but maybe the thing was deleted or was modified. But yeah, Conda-forge gives this guarantee. Yeah.
In the pixi.lock file, if you have a story to like a historical of all the packages, for example, I began with the version of Python 3.1, or I switched to the 2.5 and I switched to 3. Like we can have the historical of all the changes that we have. We did it.
So you don't have it in the pixi.toml or in the pixi.lock file. You don't have it there. But if you put these files into version control, so using Git, that you will see in half an hour, then Git has all the history, and you can go back to previous versions and see what you had at the moment and reproduce exactly those environments if you need to. So that's a different topic, which is handled by version control system, and Git will be presented in the next lecture.
Okay, so to conclude, what is the main difference between Conda and Pixi? It's we can see all the packages that we can see in Pixi and not in Conda version.
Yeah. So the ecosystem is the same. The dependencies that you actually get are the same. They come from Conda-forge, so this is the same. The difference is with Pixi, you get the log file, which means you can reproduce any environment that you manage to specify. With Conda, you don't have this, so you have the problem that we talked about before, that in 2 years, maybe you cannot make the same environment. You want to reproduce your result, you want to recreate the environment, you cannot because the things broke down and were not carefully specifically written. So that's what you gain using Pixi is the log file. There's also a difference in the way they work. So it's this workspace design of Pixi is that you work only on a workspace in a specific location. Conda had this global environment basically that you could use everywhere. Pixi doesn't really have that. There is global environments, but it's not really recommended to work on a project to use them. It's more to install tools globally. So that's a different design decision from the Pixi, and yeah. You have to learn to work this way, basically, which is different than what you could do with Conda.
Okay, thank you.
To complete, Conda is two things. It's a format for repository and package, and it's a tool, Conda tools. So Pixi use the package repository, but replace the Conda tools. You know, you can have Conda, Mamba, Micromamba, all these kinds of clients for to access to Conda repository package.
Yeah, yes. Exactly. Thank
you. You can use Conda package, but you replace the Conda tool with something more quick and quicker and with lots of function.
Just a question about some module which is only available with pipe, for example, torch. You cannot install torch with Conda, so you need to install torch with pipe.
It's actually available, but it's packaged by the community, so it's not recommended by the PyTorch maintainer. So if you speak about PyTorch,
yes, I talk about PyTorch.
So you have Conda packages for PyTorch on Conda-forge, but they are packaged by people from the community, not by NVIDIA themselves. Not NVIDIA, sorry, by Meta themselves.
Yes.
So you can use Conda packages for PyTorch. You can also use PyPy dependencies in Conda environment using pixi. So this I didn't show, but let's say we want to add PyTorch, you could do pixi add, then you specify, I think, PyPy like this, and PyTorch. I think that's
so
the syntax.
that use pipe to install.
Yeah, it would take. It's a bit complicated. It would look at the dependencies of the PyTorch package. If some of those dependencies are available in Conda ecosystem, in Conda-forge, it would use these and not the PyPy dependencies, because it's trying to not mix too much PyPy and Conda, because that usually creates issues. And what is not available in Conda-forge, then it will get from PyPy and install them also in the virtual environment. So Conda also had this thing. You could have pip dependencies in Conda environment. Pixi allows you to do the same. And so it creates a torch. Okay, yeah, in Lua, I don't know if it's available on Conda-forge. Yes, that's just a name difference between the packages. The Python package is called Torch. The Conda package, which is the same, is called PyTorch.
Now you install from PyPy, and the PyPy package PyTorch, if you look it up, it says, please install Torch. So you didn't install anything, you installed an empty package.
This one is not, okay.
Says, please install Torch.
It's been a while since I installed it.
And now you get the...
Because I have the other one, so I need to remove this maybe.
And the Torch fields are not on PyPy for GPU, right? The problem is that they dropped support for the old macOS architecture.
Okay.
Is there anyone here who still has an Intel Mac? Because I think these are mostly phased out now, right? And many people dropped support for the OS x64 architecture now. Because most people have the at least M1 MacBooks or newer.
So anyway, I think the answer is that you can get things from PyPy, provided they are available for your platform. Yeah. We are a bit late. Lots of questions, but that's good. So I'm gonna skip. Normally we had a little session now about good coding practice. I'm going to skip it. We will talk about it during the exercise session. Basically, this entire school is about good coding practice, right? When you learn about Git, you learn how to share code, how to write good informative commits. That's good coding practice. Then we talk about test tomorrow. Same thing, it's a good coding practice. So I don't have, this entire school, you will be taught good practices, basically. So I will just keep it for now, and we talk about it later. Those are more programming good practices, programming design good practices. Sometimes it depends on the language, on the application, so I think we just keep it, right? So I go over, we talk about it this afternoon. And I go to the last part of this, which is about project structure. So what we had at the beginning and we have now, basically, is something which is very flat, which is just, we had the CSV file, the Python script, and the README. That was very simple, so not hard to parse from people, but as the project grows, it's a good thing to organize it better so that you can easily find what you search. And also, most projects are organized the same way because some part of the organization depends on the language. You need to organize your code in a specific way to make a package, for instance. And so people are used to these structures of project, and using the structures in your own doesn't require much work and makes it much more easy for other people who come in to understand what's going on and to get started with collaborating on your code maybe, or just looking at it and understand it. So the recommended organization would be something like this. It's a recommendation from the Everse project. You put everything in one repository for all your code. If you want to put your results and your data inside the project, you can do so, but you should organize it in a specific directory so that it's clear, and as it grows, you make more studies, you start to have more results, so keep these things organized. I must say that you can only use efficiently Git to store data if the data is really small, basically. So that's not a recommendation for any project. It's for very small analysis, like the pcoffee, it's fine. As things grow, you want to use a separate solution to store the data, which are too big to be handled with Git, basically. Makes things impractical. Few megabytes starts to be annoying. You have to think that this goes into Git later on, and then every time someone clones your repository, it has to download the stuff. And with Git, the history is stored as well. So if you make a modification to the data, you push it, now you have it twice. You have the old version, you have the new one. So this with Git LFS, you can manage so it can be, you can still manage with more than a few megabytes, but I would say start to think about it early and use a proper solution if you have something which is a bit bigger. You should also document what's inside your package, right? So you can have a documentation directory which contains code to generate the documentation from the code, for instance. Something will be shown in a lecture during the school also, so you will see then. If you want to put the results also, you can use a specific directory. That's the same thing. If you just do one small analysis and you have one set of results, it's fine to put them in the repository. If you have a more advanced study, basically you implement a package to make an analysis, but then you will make several analyses on several datasets, etc. Maybe it's best to put the results in specific dedicated repository, one for the analysis on this dataset, one on this one on this one, etc. So it's, again, up to you to determine whether or not these things will grow out of control or not, basically. And so the results, etc. And then for the code, basically, the recommended thing is to structure it as if you would be doing a package in the specific language that you are using. So for us, it's a Python package. So far, we just had the main.py script, so it's just a script that you can execute with Python. But if you wanted to make this a library that other people could use as a dependency, you will need to make this package, basically. That's what the package is. And the recommendation is to structure your project as if you would produce this package for other people to use. Maybe they don't. Maybe there is no need. But if you do it from the start, it's done. You are ready if you ever need to use it. And this organization is extremely common, so people are not lost when we come to this.
Question is not really related, but is there a tool that is equivalent to the make?
Yes.
In order to, let's say, because you have this kind of architecture, and you would like to create a manuscript from all the things that you don't want to redo all the things.
Yes.
Because only few files were modified. So
Yeah.
Is there with Pixi something equivalent?
Yes, it's the Pixi tasks, which are basically make, in fact, but when you execute a command, it gets executed in an environment that you specify. So you add tasks per features. I will not show any now, but tomorrow for the test, we will introduce a task that executes the test, for instance, that you can use like this. So yes, it would be the Pixi tasks. Yeah.
Just if you go up for the SRC folder, you know, in the literature, I see that sometimes you can have SRC and not pcoffee, just SRC, and sometimes just pcoffee and not SRC.
Yeah, so you have different layout possible for Python packages. You have the flat layout, which would be just pcoffee and no source. This is the so-called source layout, so you have source and then the package inside. I would recommend you to use the source layout even though you can. So the others also work, but with the source layout, basically you avoid sometimes trouble. You have less chance that the imports of your Python files work when they should not. So basically you catch problem early. So I would recommend to use this one.
Yes,
but others also exist and can be used.
I've seen in literature, but when I check lots of package, there is some they just make the SRC and not the pcoffee folder. So
underneath. Okay. Well.
Okay. So
if it works, it works. Okay. So as I said, we should probably structure our code as if we were going to make a package. So since we're working with Conda, we need to make a Conda package. Conda has a bit of this overhead because it's language agnostic. So basically, the way a Conda, what is a package? What is a Conda package? It's an archive like any package. So it's just a compressed archive containing the files. And when you install the package, what you do is you take this archive, you extract the files inside, and you put them in the environment, the Conda environment. You put them in the right place. So if you make a package, if you make a package that just have a binary, for instance, in your archive, you would have some metadata for Conda and the binary. And when you install the package, basically the binary gets copied there. If you have Python files, basically they go inside lib, Python side packages, that's where Python installs its dependencies, and it goes inside. So that's basically what is a package is just an archive, and what is installing a package is just copying what is in the archive in the environment at the right places. So how a Conda package is made, it's a funny solution they chose is because they want to be language agnostic. They don't want to have specific support for every specific languages. So the way they manage to make Conda packages is like this. They create a virtual environment for you during to prepare for the packaging, and then they tell you, okay, just install your software in this virtual environment that we provided for you. Do this whatever you want. If you're using Python, you use the Python tools. If you're using C++ with CMake, you use CMake, etc., etc. So this is your problem. We don't care. Just use this virtual environment, install inside. Once the installation is finished, the build tool of Conda is going to look inside the environment at what new files are there that wasn't there before. Basically, these new files are taken and make into an archive, and that's the Conda package. Pretty simple way of doing things. In truth, it's more complicated than that because they want to make the installation relocatable, so they need to remove absolute paths and links, etc. So there is some patch on the file which is done, but that's basically the idea. And so for us, what it means is that if we want to make a Conda package, we first have to make a Python package so that we can install our things in a virtual environment. We could do it by hand, but of course the much more easy way to do is to use the Python packaging tools. So the first thing we need to do is to structure the code with the source layout, like I was saying. So we'll just create the source and pcoffee repository, and I will move the main.py inside. Okay, so now we have this source, and inside we have we have the pcoffee, and inside we have the main.py file. So I just moved it. Yeah.
In UV, there is an option to create sort of package already architecture.
Yeah,
you have the same in Pixi.
Well, Pixi is Conda, so it's independent of the language. So you don't have something specific for Python to create the architecture. Yeah, so, but you can use UV if you want to make the folders. I mean, it's not here I do it by hand because it's just one file. But yeah, sometimes you want more things. Then what we need to add is a PyProject file, so a TOML file, which is the way Python packages are described. And this, so basically Python packaging is a pretty complicated topic in itself, so I won't go into details. But the first thing you need to specify is a build backend for your package. So the historical one, and maybe one that you've seen, is setup tools, but there are others build backend, which have been made to make things easier than setup tools could. And the people from UV, they implemented the build backend UV build, so here we are going to use this. That's the most basic PyProject file you can have. Usually, we include in this file a few metadata for the package, so that when it ends up on PyPy, people have some information where it's coming from. So it would look like this. You say the name of the package, maybe the version, a small description. You can include your README so that it's shown, minimum Python version, etc., etc. So that's just metadata for the packages, basically, but nothing else. I think that's all we need to make the Python package, the Conda package. So we'll try to build it now using UV. So I'm going to install UV and see if we can make the Python package. So here I'm using the global install thing. See, it's the global environment of Pixi, which is typically used to do this kind of thing, so to install tools that you need to use more or less globally. We won't be needing UV then for the Conda packages. It will be hidden in, below Conda, so I will be able to remove it. This is just for the demonstration. So I forgot something. Yes, Python packages, Python modules, they need to have this init file so that the interpreter knows it's a package, basically, so we can look at the modules inside the directory. That's it. So now it works. In Python, you have two types of packages. You have the source distribution, so sdist called, which is an archive of the sources, basically. So when you have pure Python, it's the Python files, but when you have also like C++ wrapper is in Python, all the sources get put inside the file. And when you want to install it, the Python package tool that you use to install is going to compile what needs to be compiled and copy the rest to where it needs to be. Using the source distribution only is not recommended because this installation step can take some time, and if you have a big stack of dependencies, it can take a lot of time. So that's why in Python they also invented the compiled artifact distribution, if you want, which is called the wheel. So it's this one. That's why we have the two packages, basically. And the wheel file is the thing already compiled, so when you install it, you just need to copy it at the right place, basically. The wheel, of course, is platform-specific, where the platform-specific if it contains compiled code, when the source distribution is not. So the recommended thing, which is handled automatically for us by UV, but I'm just explaining it for you, is to have both. So when you upload to PyPy, for instance, you can provide the wheel and the source distribution. People that are on a platform for which a wheel exists, they will use the wheel directly and the installation will be fast. People who are on a platform where the wheel doesn't exist, they will get the source distribution and recompile, basically. That's the way you can get the best of both worlds in the Python ecosystem. So now we have our Python package ready. We can try to make a Conda package out of it. So for this, we need to modify our pixi.toml a bit to include the package section. So the package section looks like this. It's the Conda specification for a package, basically. So it's a bit similar to what we have in the Py project. I will add it here. Doesn't really matter where it is. So it's kind of the same thing. We have the package name, version, offer, etc. It's the metadata that we also had in the Py project. Pixi is actually able to extract the metadata from the Py project, so you don't have to repeat. Here I just copy it over. Then we are going to specify a build backend again. This is the Conda build backend, which tells Pixi which tool to use depending on the programming language. So here we use Python, so we use the Python build backend for Pixi, which is itself going to call the Python build backend that we had in the Py project, so the UV one. You have a cascade of backends that call each other, basically. This is the one for Conda, the other one was the one for Python. Conda packages, they can be specified for code that you compile. So if you need some build tools like compilers, make, these kind of things, you can specify them in the build dependencies. For Python, we don't need. We're going to use UV as a tool to make the package, but we need to make it in the host section so that the paths that UV creates, they correspond to the host environment, the one on which we're going to install. And finally, we put the dependencies of the package in the runtime dependencies. So that's the dependencies that we had here in the dependency section in our default environment. So now that we have the package section, we can remove them from here, basically, and we can add a dependency on our local package. So I think the syntax is this. Let me check, yeah. So what this says is, okay, in our workspace, we build a package. In our default environment, we had the dependencies that now they are set in the runtime dependencies of the package. So in our default environment, we just specify this package. It will be installed. And when it's installed, these dependencies will also come with. So we don't have to repeat the dependencies specification. They are included with the package, basically. I think that's all we needed. So now we can try to build the Conda package. Yes, sorry. So I forgot something, but to use the build, to use the pixi build feature, we need to add this to the workspace configuration. The build backends are called the preview feature, so it's quite new and it's not available if you don't specify this. Okay. And now basically it works. So we successfully built our Conda package. If we look at the output here to understand what's happened, it's what I described before. Pixi is creating a virtual environment for the package creation. So it's a separate one than the one we had, the default prod, etc. It's a one just for building the package. Inside is going to put the tools that we requested. So we have UV and UV build, which were in the host dependencies, plus another environment for the runtime dependencies. So that's Pixi preparing the virtual environment for us to install the Python package inside. Then the hand is given to the Python build backend, which is going to call UV build, so the build backend of Python, to install our code inside the environment. So this is the output of UV, which is in verbose mode, so there's a lot of stuff, but basically it's going to build the Python package, the wheel. And then it's going to install this wheel inside the virtual environment created by Pixi before. And finally, once this is done, the Pixi build command, it looks at what are the new files in the virtual environment created to build the package. We have the list here. This is put inside the Conda package, and that's our Conda package, basically. That's how it works. So now we just have the Conda package here locally. The extension is .conda. It's actually a zip file, so if you change the extension to zip, you can go inside and look at. Inside you have two archives, basically, one with like metadata information and one with the actual Python package and the files above, basically. If you want to have a look at, it's a zip file containing two tar archives in truth, this Conda format.
You can just call unzip -l. You don't have to change the extension or something.
It works? Okay. Yeah, so you have the metadata JSON, and then you have the two tar archives, one for the information of the package and one for the actual files of the package.
Same for the wheel, it's also just a zip file.
Also? Okay. Okay, so that's pretty much it. Now we should think probably how to distribute our code and our package. So the first question to ask is, do we actually want to do this? Is there someone that will use the pcoffee as a dependency in their code to make a new analysis? If yes, then we should make it available to them. If not, we can stop here. It's good enough. We have the reproducibility with the Pixi environment, so it's already something. If yes, and we want to do it, there is a few ways one can do this. Probably the recommended option is to put it on Conda-forge, which works a bit differently than what I just showed. In Conda-forge basically have a big infrastructure, continuous integration, that builds the packages on their own infrastructure, so you don't have to do it yourself like we did here. You just commit the recipe to Conda-forge, and then they take care of building the package and making it available to users. That's one way to do it, which is probably the recommended way in most cases. If you want more control on the build process, the build infrastructure, you can set up your own CI to create the package with Pixi build, and then you can host your own Conda channels also using dedicated tools. So the tools would be Quetz, I think it's called. Well, I don't know if it's worth showing it in any case, but you can host your own channels if you need to. If you have, I don't know, code which needs to be private and kept inside your own organization, you can set up your own Conda server hosting your channel, and you can put your packages there.
Instead of Conda, I know that we use Pixi, but if we would like to use PyPy, is it possible to send it also?
So not the Conda package, but since you have made the Python thing, you have what you need to create the PyPy package. One thing to be careful though is that here we did not put any dependency in the py.project.toml file. So the packages which is created doesn't have any dependency, which is not working in practice, right? So if you want to do both, like put the package on PyPy and on Conda-forge, or just on PyPy and you don't care about Conda, you need to specify the dependencies in the Py project to make the Python package have dependencies as well. Okay, that's all for this lecture. So is there any questions before we go to the coffee break?
Just short question. So this works for Python and other languages, I guess. But what about C++, for example, which also needs a lot of configuring?
Yeah. So what I would recommend for C++ is to use CMake to manage the installation. And there is a build backend, Pixi build backend for CMake. So then it's basically the same. You configure your thing with CMake like you would for any C++ project. And then in Conda, you just call the CMake build backend, and it's going to do the same thing it did here for Python, but for the output of the CMake installation in C++.
Okay, great. Thanks.
Last quick question.
Yeah, something. Yeah. I've seen that in the rolling notes there are some notes now. That's really nice. You can also vote for the other proposal from others. So to put your initials after the list of proposals in the checklist. And I would like to ask the speaker if you have 2 to 4 points, really crucial point for sustainability of software in this part, what should you push as advice?
You want me to answer now? Or
yes.
Okay.
If
yeah.
After you can change.
Yeah,
that's discussion, but
so the first crucial thing I think is you should include in your project the specification of the environment. That's the starting point, right? You should have something there that tells your user how they can reproduce what you do, and that starts by telling them how to create the environment. Second point is you should make sure that recreating the environment is actually reproducible. So here you want to use something which gives you this guarantee, and we've seen Pixi with the lockfile can do that. Other tools like UV can also do that, minus the issues maybe that packages are not available anymore on PyPy. But there's different ways probably to do this. Pixi for Conda and Conda-forge, this will work. That's the second thing.
Can you summarize the second thing?
It's to make sure that the specification you use the tool you use to specify your environment makes it reproducible to reproduce the environment. That it gives you the guarantee that you can reproduce exactly the same environment that you did. There are package managers that are dedicated to that, like Geeks and Nicks that we talked about a bit yesterday. With Pixi, you can do it because you have the log file. So then we've seen that the environment is not just running the software, it's also developing it, so you need to connect it to your IDE. So just do that. Basically, it depends on the IDE you use, but that's also something you will need. And finally, you should structure your project as a common way people structure any programming project for your language, basically. So if you put the result and the thing, you follow the structure that we had discussed before, like this. And you should probably, we would recommend, it's not probably, it's recommended that you structure your code as if you were going to make a package in whatever language you are working with. So for Python, use the source layout like this to make a Python package. You don't actually need to distribute the package, but if you organize like this, you will be able to distribute if you need to in the future. And people that come and they see these kind of things, they understand it because it's extremely common.
Yeah, with the advice in the notes, please have a look and correct me if it's not right.
Okay, perfect. Thank you.
Thank you very much.
And I just add, test your package and your code in a very new server or compute, because you have you build environment, you have very low level dependencies, and sometimes the C compiler is not exactly the same, and what you produce is not compatible. So it's okay on your computer, but if you...
With Pixi, you would be using the compilers coming from Conda-forge, basically.
Yes, but I've got the...
Yeah, no, I agree with you. We didn't talk about test now because it's the future lecture, but this kind of advice, yes, they will be given.
Even Conda package doesn't work on any computer. Sometimes it happens. So if you want to be sure, take a right new computer and try your production.
Okay, let's have the break now. Thank you again, Vincent. So we meet in 15 minutes.